The borough of Manheim's wastewater treatment plant is located approximately 11 miles north of Lancaster, Pennsylvania. The plant is permitted to discharge an annual average flow of 2.3 mgd, and the peak daily flows could be as high as 4.0 mgd. Since the plant discharges into a tributary of the Susquehanna River, it had to be upgraded to meet the new discharge standards as required by the Chesapeake Bay Initiative.
Manheim Borough Authority underwent the upgrades of our wastewater treatment facility for reduction of nutrients to the Chesapeake Bay and its tributaries. The treatment process that was selected was the Bio-Denipho system from Kruger. The upgrades consisted of 2 Kruger phase oxidation ditches with anaerobic selectors and post-denitrification, along with 2 additional clarifiers.
Ritu, the borough's engineer, was tasked with designing an upgrade for the plant to meet the requirements set by the Chesapeake Bay Initiative.
Because of the Chesapeake Bay strategy, we were required to look at alternatives in order to meet the Chesapeake Bay strategy, which required us to meet 6 milligrams total nitrogen and 0.8 milligrams total phosphorus. We've prepared an exhaustive study on behalf of the authority, and after looking at various alternatives, we identified that the Kruger phase oxidation ditch was the technology that we wanted to go with. Kruger has a proven track record in the wastewater market. We have about 100 of these or so oxidation ditches, and I believe they are the firm to work with for these types of ditches. This plant has been operational now for about 2.5 years, and you can see the oxidation ditch here behind me. What's really nice about this oxidation ditch is that it's a phased oxidation ditch, which means that we can control both the aerobic and anoxic zones as we need to, and because of that, we've been able to achieve some remarkable total nitrogen levels. As I said, we had designed it for 6 milligrams per liter total nitrogen. I'm proud to tell you today that we're actually less than 2 milligrams per liter total nitrogen.
Design began in 2005. Bids were opened in May of 2011, and the project came in below the engineer's estimate of $9.3 million. The notice to proceed was given to the general and electrical contractors in September of 2009, and startup began in the spring of 2011. Wastewater from the collection system is first screened before being pumped into the Bio-Denipho process. The first biological process is an anaerobic selector, utilizing the 3-stage block and hong process for biological phosphorus removal. To ensure optimum biological phosphorus removal, return activated sludge, or RAS, is pumped to the first stage of the block and hong selector, where any nitrates and dissolved oxygen and the RAS are removed by the bacteria. Raw influent is then introduced into the second stage. By the time the wastewater and RAS enter the third stage, the wastewater is fully anaerobic, and optimum selection for the growth of phosphorus accumulating organisms is achieved. In addition to phosphorus removal, the anaerobic selector prevents the excessive growth of filamentous bacteria that are often responsible for poor settling characteristics and secondary clarifiers. Use of the selector results in the formation of a dense, rapidly settling flock that is low in filamentous bacteria and leads to increased RAS-WAS concentration and decreased RAS-WAS pumping. The effluent from the anaerobic selector then flows by gravity to an influent distributor, which has a motor-operated gate that directs the wastewater to one of 2 reactor basins. This simple and low-maintenance device creates an alternating flow pattern into the main biological reactors. Effluent from the reactors flows to the secondary clarifiers and is also controlled in the Bio-Denipho system. Here, each reactor is equipped with an electrically actuated weir that either stops flow from exiting a reactor when fully raised or allows flow to exit the reactor when lowered. Combined with periods of alternating aerobic and anoxic conditions achieved by independent operation of the aeration and mixing equipment, the alternating flow paths allow the Bio-Denipho phased isolation ditch process to achieve enhanced nitrogen removal to very low levels without internal recycle piping or pumping. Unique ability to utilize the entire tank volume in either aerobic or anoxic mode and adjust the specific phase lengths enables the phase isolation ditch to accommodate a wide range in influent flows and characteristics resulting in tremendous process flexibility at maximum process efficiency. Aeration is provided by Kruger's brush aerators, though other aeration configurations are available. Kruger's brush aerators are unique in that they are installed under a bridge, which reduces noise and aerosols while still allowing easy access to the equipment. The motor is directly coupled to the gearbox, is also accessible from the walkway, and features Kruger's precision-engineered enclosure to protect the motor and further reduce noise. The phase isolation ditch is automatically controlled by a state-of-the-art PLC system and has the ability to allow for manual operation of each and every component as needed. The PLC-based control panel also includes pre-programmed operational modes, such as the stormwater mode for peak flow events. This mode can be activated manually or automatically, and will incorporate a settling phase into the Bio-Denipho process to prevent solids washouts from the clarifiers during severe rain events. To ensure economical and efficient treatment, the control system also controls the aeration equipment by automatic dissolved oxygen control. DO probes continuously monitor and report residual DO levels within the oxidation ditches to a PLC-based control panel that controls the aeration equipment to meet but not exceed the current oxygen demand. This control eliminates costly and wasteful over-aeration. The control of the alternating flow paths in aerobic and anoxic conditions in the reactors is traditionally accomplished through the adjustable time-based settings in the PLC. However, Manheim selected an advanced controls option that further automates the process through the use of Kruger's Superior Tuning and Control, or STAC system. The STAC system uses online monitoring of ammonia and nitrate in the reactors and makes process decisions automatically to simultaneously maximize both nitrogen removal and overall process efficiency.
The real-time monitoring of ammonia and nitrates enables automatic phase control, which helps reduce operator continuous monitoring and adjustments. These adjustments are made in real time throughout the day, allowing for much better and more consistent treatment.
With a favorable BOD to nitrogen ratio, phase isolation ditches can produce an effluent total nitrogen concentration of less than 5 milligrams per liter. But since Manheim had to meet an annual average total nitrogen limit of 3.2 milligrams per liter, a secondary anoxic zone with supplemental carbon addition was also included in the system, where the bacteria converts nitrates into nitrogen gas. To help reduce the amount of supplemental carbon required, the Manheim wastewater treatment plant incorporates Kruger's patented RAS bleed process. The process increases the mixed liquor in the secondary anoxic zones by 20 to 30%. Studies have shown that the bacteria in the RAS being returned to the secondary anoxic zones have already adapted their metabolic pathways to utilize nitrates, and that some BOD that was released in the clarifier sludge blanket is also returned with the RAS. Plants with this process have found that they produce a final effluent with a total nitrogen concentration of even less than 3 milligrams per liter without supplemental carbon addition. This feature, when combined with the online nutrient monitoring of the Kruger STAC system, makes the Bio-Denipho the most efficient nitrogen removal system on the market today.
One other benefit of the Kruger system is the STAC, which is actually, I'm standing here beside me. The STAC is a system which is an inline monitoring process which actually monitors continuously the nitrates and ammonia nitrogen against various set points. And because of that, it's really helped to save lots of energy. We really haven't done an alternatives analysis, but we believe that we could probably get about 30% reduction in our power just because this monitors the entire process. And once we've established or hit the set points, it turns the equipment off or turns the equipment on. It really acts like another operator. So I think this was a great idea to include this as part of the project. You know, when we started designing this project, I believed that we had chosen the right technology in working with Kruger. Now that we've been online and we've meeting these fantastic limits, I really know that we made the right choice.